Hey there, welcome back to Honors Chemistry. Today we will be talking about atomic structure and electron configuration. This is going to be topic 2 of Unit 1. And I just want to inform everyone that I know it's been a minute since I posted, and I'm really sorry about that. But while I was on spring break, I was just taking a little time to recharge, and while I was gone, I did brainstorm some new fresh ideas for my videos. So definitely no more slacking. And I'm going to be posting more consistently this week, and I promise on that. And today, this video is all about atomic structure and electron configuration. And for some of you guys, I know that sounds super complicated, but don't worry, I'll break it down and make it way easier than it sounds. Let's just think of this as a chemistry adventure. We're going to be exploring atoms like we're tiny explorers in a super cool world. And don't worry, no microscope needed, just a little brain power. Alright, let's dive right into it and see what atoms are all about. Okay, so atoms are like the building blocks of everything around us. You've got protons, neutrons, and electrons. Kind of like the cast of characters in an atom story. If atoms were a Netflix show, protons would be the main character. Neutrons would be the background actors, and electrons, they'd be the social media influencers, constantly on the move. Electrons are the only ones who interact with other atoms and cause all the chemical reactions. The number of protons in an atom determines what element it is. Neutrons are just kind of hanging out, not really affecting the element, but electrons, they're what really determine how atoms react. Think of them like the wild cards in a deck of cards. They make things interesting. Let's dive into the next slide and see what these subatomic particles really do. Alright, let's zoom in and talk about the three key particles that make up an atom. You've got protons, neutrons, and electrons. But what do they really do? Protons and neutrons move in the nucleus, which is the center of the atom, while electrons are off on their own little adventure around the outside. Well, to restate it, basically, protons and neutrons are the parents, and the electrons are the rebellious teens who can't stand still. But seriously, each particle plays a unique role in the atom, and without them, we wouldn't have the elements we know and love. Alright, let's break it down so you can picture how these guys fit into the atomic world. Protons are positively charged and live in the nucleus. Neutrons are neutral and also live in the nucleus. The electrons are negatively charged and orbit the nucleus in energy levels. The number of protons defines the element. Alright, so protons and neutrons are heavyweights, chilling in the nucleus like the strongest players on the sports team. They don't move around much, they just stand there flexing their atomic muscles. But electrons are the complete opposite. They're just zipping around, hanging out in energy levels, kind of like levels in a video game, like Dragon Ball Z, if you know what I mean. But the number of protons determine what element the atom is. It's basically like a name tag for the atom. If you change the protons, you get a totally different element. It's basically like trading Pokemon cards. Neutrons don't mess with the identity of the atom, but they can change the isotope. That's like the variant of an element. So yeah, while protons are the VIPs, neutrons are just the quiet ones in the background. Let's keep going and talk about how electrons are arranged. Alright, slide 3. Energy levels and orbitals. Now that we've met the protons and neutrons, let's talk about how the electrons and how they're arranged. Alright, so electrons live in energy levels, which you can think of like floors in a building. The closer the electrons are to the nucleus, the lower their energy is. And the farther they are, the more energy they have. Basically, it's like your phone. The closer you are to a charger, the more battery you have. Electrons don't just hang out anywhere. Though they are in orbitals, basically their own little assigned zones in each energy level. And the way these electrons are arranged can tell us a lot about how atoms behave. Let's take a closer look at how these energy levels work. Alright, so electrons are arranged in energy levels around the nucleus. Energy levels closer to the nucleus have lower energy. Electrons can only exit in specific orbitals in each energy level. These orbitals help determine how atoms bond and react. Okay, so electrons are basically the rock stars of the atom. They need their own space. Just imagine how each energy level is like a floor of a building. Electrons aren't allowed to float around aimlessly like they're lost in mall. The lower floors, which is closer to the nucleus, have less energy, while the higher floors are packed with more energy. And just like how they're assigned a seat at each concert, electrons sit in specific orbitals. These orbitals determine how atoms interact with each other, especially when atoms bond. It's like electrons are picky about their seats. They won't just sit anywhere. So, the way electrons are arranged is super important for chemical bonding. Let's talk about how these arrangements help atoms behave. Alright, so now that we know about energy levels and orbitals, let's talk about electron configuration. This is just the way that electrons are arranged in an atom. I know it sounds a little super fancy, but it's just really just figuring out where the electrons sit in each energy levels. Think of it like a seating chart at a party. The electrons can't just sit whatever they want. Imagine the chaos if everyone sat wherever they felt like it at your birthday party. Let's see how these seating arrangements work in an atomic world. The electron configuration show how many electrons are distributed in an atom. Electrons fill lower energy levels first before moving to higher ones. The periodic table helps predict electron configuration. Understand electron configuration help explain atomic behavior. Electron configuration is like the seating chart for electrons. If you're planning a party, you've got to put everyone in the right spot, or things could get messy. Electrons fill up the lower energy levels first, just like how you fill a smart pool before you jump into the deep end. So we can use the periodic table to help predict how electrons are arranged, which is super handy for figuring out how atoms behave. Basically, it's like the periodic table is in the cheat sheet for atomic behavior. Understanding electron configuration is key to knowing why atoms act the way they do in chemical reactions. So now that we have the scene chart, let's move on to how this affects bonding. Alright, so now we know that about electron configuration, but how does it affect bonding? Well, atoms bond to fill their outermost energy level with new electrons. This is like the final touch to complete their octet, which just means 8 electrons in their outer shell. Atoms are like that person at a party who has to be with a cool crowd. They just want to be surrounded with the right number of people. When atoms bond, they either share or transfer electrons to fill their outer shell. And let's break down how this works. Atoms bond to fill their outermost energy level. Electrons are shared or transferred in bonds. Covalent bonds share electrons. Ionic bonds transfer electrons. The goal is to achieve a full outer energy level like noble gases. So atoms are always trying to complete their outer shell. Think of it like a group project where everyone just wants to get their perfect score. Atoms can either share electrons, which is covalent bonds, or transfer them, which is ionic bonds, to fill the outer energy level. The goal is to be like noble gases, who have a full outer shell and are basically the coolest atoms in the periodic table. So whether our atoms are sharing or taking electrons, it's all about filling that outermost shell. It's like being at a party and everyone wants to sit in the VIP section. Let's see how these bond forms in compounds. Let's talk about the two main types of chemical bonds, covalent and ionic. Both happen when atoms try to fill their outer energy level, but when they do it in different ways. In a covalent bond, atoms share electrons like they're passing around a cool new video game. It's like basically buying your friend's pencil. Hey, I just need it for a minute. Ionic bonds are a little different. One atom basically takes electrons like they're grabbing the last slice of pizza at a party. Let's dive into both. Covalent bonds share electrons between atoms. Ionic bonds transfer electrons from one atom to another. Covalent bonds usually happen between nonmetals. Ionic bonds usually happen between metals and nonmetals. Alright, so covalent bonds are like trading your favorite snacks with your friend. You both get what you want. In other words, you're both sharing to make sure no one leaves hungry. Ionic bonds are the opposite. They're like that one person who swoops in and takes the last piece of pizza without asking. It's like a game of finders keepers, but just for electrons. Covalent bonds happen when nonmetals share, while ionic bonds usually happen when metals and nonmetals. So whether you're sharing or taking, bonding is all about making sure everyone is happy with their electrons. Let's keep going and look at that compound. So now we know about bonds. Let's talk about molecular compounds. A molecular compound is a substance made of two or more atoms bound together. You can think of a molecule like friendship group. It's made of different personalities coming together to create something awesome. Atoms form these compounds to achieve a stable electron configuration. It's kind of like how you want to get an A on your test, so you study with your best friend. But in chemistry, like studying is the bonding, and the A is achieving that stable configuration. Molecular compounds are made up of two or more atoms bonded together. These compounds form when atoms share electrons. The shared electrons help atoms achieve a stable electron configuration. Molecular compounds typically form between nonmetals. Alright, now that we know how molecular compounds are formed, let's talk about their properties. These compounds tend to have lower melting points and boiling points compared to ionic. Molecular compounds are like the chill group of atoms that just want to hang out in a comfortable temperature. They don't need high heat to break up their bonds. They also don't want to conduct electricity as well, because they don't have free electrons to move around. Imagine being at a party where Wi-Fi is so bad nobody can use their phones. That's basically how molecular compounds feel about conducting electricity. Let's move on to these properties. Molecular compounds have low melting points and boiling points. They don't conduct electricity as well as others. They tend to be gases or liquids at room temperature. Their bonds are generally weaker than ionic compounds. Molecular compounds are super chill. They don't need high heat to melt or boil. Unlike ionic compounds that need a lot of energy, they're the laid back atoms at a party who's like, nah, we're good. We don't need to heat things up. These compounds are usually gases or liquids at room temperature because their bonds are weak. It's like how you might not want to hold a conversation with someone who's a complete stranger. And since they don't have free moving electrons, they don't conduct electricity well. It's like being at a party with no DJ, no flow, no energy. But even though they're relaxed and non-conductive, molecular compounds are still super important. So let's move on and look at a different type of bonding. Next up, we're going to talk about ionic compounds. These are the complete opposite of molecular compounds. Ionic compounds form when one atom steals an electron from another. It's like a sneaky theft at a school cafeteria. Yeah, it's like grabbing someone else's lunch when not looking. This happens when metals and nonmetals, with metals giving up electrons and nonmetals taking them. Metals are like, here, take my electron, I don't need it. And nonmetals are like, thanks, I'll take it. These compounds are usually pretty solid and have a high melting point because of the strong bond between the atoms. Let's dive in deeper. Ionic compounds form when electrons are transferred from one atom to another. Metals give up electrons and then nonmetals take them. These compounds form between metals and nonmetals. Ionic compounds usually have a high melting point and are solid at room temperature. So, ionic compounds are like the total opposite of molecular compounds. They form when one atom completely gives up an electron. Kind of like one-sided transaction. Imagine a trader and one person giving away their last snack, and the other person is like, yes, I'll take that. Ionic compounds form when metals, the electron givers, and nonmetals, the electron takers, come together. Because the bond between their atoms are so strong, ionic compounds have high melting points. They're tough cookies to break. It's like trying to break in a super secure vault. These compounds are usually solid at room temperatures because of their strong bonds. Well, let's keep going and learn how these ionic compounds behave. Whoops. Alright, let's now look at the properties of ionic compounds. These compounds have really strong bonds, which means that they have high melting and high boiling points. Ionic compounds are the bodyguards of the chemistry world. They're tough to crack. Since they have changed particles that can move around in a solution, ionic compounds can conduct electricity when dissolved in water. It's like when you got a friend who can't stop talking and suddenly they're a human megaphone. Ionic compounds also tend to be hard and brittle, like your own phone screen that crack when you drop it. So, let's break down their properties a little more. Ionic compounds have strong bonds, so they have high melting points and boiling points. They conduct electricity when dissolved in water. They're usually hard and brittle. Ionic compounds are often crystalline solids. Ionic compounds are tough, like the bodyguards of the atomic world. They don't break easily because their bonds are super strong. It's like trying to break into a bank vault with a paperclip. It's just not happening. These compounds also conduct electricity when dissolved in water, which makes them super useful for things like batteries. Sorry, I just said butters on accident, sorry. I meant batteries. It's like having a phone that only works when plugged into a charger, but for atoms. That's usually hard and brittle, which is why they can easily crack if you drop them. Ionic compounds often form crystalline solids, which are just fancy ways of saying they form nice, neat crystal structures. Pretty cool, right? Now let's move on to the last slide and wrap this up. Alright, let's wrap it up with some key takeaways. We've learned a lot about atomic structure, electron configuration, and how atoms bond to form different types of compounds. It's been a bit of a roller coaster, but I promise no need for seatbelts. Remember that atoms are made of protons, neutrons, and electrons. The electrons determine how atoms bond, and that's what makes chemistry so interesting. We also learned that about the difference between a molecular and ionic compounds, and why ionic are so tough when molecular compounds are a little more chill. Let's hit those final thoughts to finish strong. Atoms consist of protons, neutrons, and electrons. Electron configuration determines how atoms bond. Molecular compounds share electrons and tends to have low melting points. Ionic compounds transfer electrons that are high solid and have a high melting point. So basically, atoms are made of protons, neutrons, and electrons, and the way those electrons are arranged determines how atoms bond. Think of it like choosing which your friend gets to pick the playlist. That's how bonds are formed. Molecular compounds share electrons, while ionic compounds transfer them. Ionic compounds are solid and tough, while molecular compounds are a little more laid back. Just remember, all of this is about helping us understand the world at a tiny microscopic level. Chemistry is cool, and you're now one step closer to master it.